Okay, now that we have looked at the decimal number system that has digits 0 through 9, let's look at the binary number system. The binary system has a base of 2, which means we only have two possible digits, 0 and 1. Each digit is referred to as a bit, and a bit is used as a computer's most basic unit of information. When we talk about a nibble, we're going to be talking about 4 bits, and a byte will be talking about a group of 8 bits. The rightmost bit of any number is the least significant bit, as seen in this example, and the leftmost bit is always the most significant. So just like with our decimal number, the leftmost digit has the highest contribution, or is the most significant, and the rightmost has the smallest contribution, or is the least significant. As before, each digit position has a weight, but this time, instead of our weights being powers of 10, like they were in the last example, our weights will be powers of 2 because we have a base 2 system. Let's look at this number. First, notice that we have 3 dots out in front, leading zeros, and for that matter, these 3 zeros will not affect our number in any way. The rightmost digit or bit has a weight of 2 to the 0, which equals 1. The next digit to the left, or bit to the left, has a weight of 2 to the first, or 2, followed by 2 squared, or 4, 2 cubed, which is 8, 2 to the fourth, which is equal to 16, 32, 2 to the sixth, which is 64, 2 to the seventh, which is 128, 256, 512, 1024, 2048, and this could go on and on. But again, notice that our weights are powers of 2, starting with the 0 power for bit position 0. This 1 on the right-hand side is considered to be the least significant bit in the bit 0 position. The subscript 2 at the end of this number, again, is to indicate that it's binary. It's optionally used to indicate the base. Before we start looking at other number systems in more detail, let's observe some of the patterns when counting in binary. Notice that this rightmost column changes from 0 to 1 every other bit. Every 1 bit it changes from a 0 to a 1 and a 1 back to a 0. But the next column to the left changes from 0s to 1s every 2, or 2 to the first. So we have 0, 0, 1, 1, 0, 0, 1, 1, and so on. The third column to the left changes every fourth number, and then the fourth column, or the most significant column, changes every 8. If I had a fifth bit, it would change every 16, and so on. So again, these patterns coincide with the powers of 2 that provide our weights. And again, notice that our counting, even in binary, always starts with 0. The 4 zeros up here are equal to 0. We have 1, 2, 3, 4. In the next node, we'll discuss conversions from binary to decimal in more detail. But for now, notice the patterns as we count from 0 to 15 with these 4-bit examples. Another positional number system that we use is octal. Octal is a base 8, or a radix 8 positional numbering system. The octal number system has 8 possible digits. And these are 0 through 7. Counting in octal then means that once we get to 7, there is no 8. We have 8 digits, but we start at 0. So once we get to 7, we have to wrap back around, and 10, 11, 12, on up to 17, and then we go to 20, 21, on up to 27, and so on. There's also a number system called hexadecimal, which is a base 16 positional number system. There are 16 possible digits. The first 10 of them are the 0 through 9 that we use in our decimal system. However, once we hit 9, we don't have any more numbers, so we start using letters. An A then will represent 10, a B represents 11, C 12, D 13, E 14, and F 15. So we have 0 through 15, or 16 possible characters in our hexadecimal number system. Counting in hex then goes 0 through 9, A through F, and then at F it goes back around to 10 through 19, and then 1A through 1F, and so on.